today and for this for the introduction. And we're not a large group. I don't feel like it's that big of a deal. If anybody wants to ask a question as I'm going, just because something seems interesting, go ahead. Like, it's fine. If I don't see, you can do the hand raise, or if I don't see your question, somebody can just interrupt and make sure we pause. This isn't going to take the entire hour, so we'll have time for questions all throughout. Okay, let's see here. So I'm talking about temperature simulation in reservoirs. It's my favorite topic, and we're going to do, and I also like water quality. So let's begin with our purpose and our outline. Today, I'm assuming that most folks in this audience are not modelers, but you might interact with modeling in a project. I don't know if we have the thumbs down availability, but I'm curious if that's generally correct. I suppose if that assumption is way out of base, maybe you can put up your hand and tell me why I'm wrong. Going once, going twice. Okay. So the purpose of this talk then is to explain the consideration and support activities that lead to a successful and useful modeling effort. I'm actually not going to talk about details of model parameterization and how, thanks, Giovanna, and how to do the different calibration and whatnot. We can certainly get into that if you want. It's very much on my mind right now for a project that I'm working on. But instead, I want to focus today more on like how to understand this modeling that we're doing, and especially if you haven't thought about it very much, or if you've heard about it, but modeling seems like a bit of a mystery, then maybe this will help give some answers to that mystery. We'll talk about temperature simulation because that's the most straightforward, but these concepts that's funny, I meant to say extend to other water quality variables, dissolved oxygen, algae, nutrients, metals, organic contaminants. Those are more complicated than temperature, but I'll mention these two here and there. And nearly everything I'm about to say applies to rivers also. My focus and my interest is more in reservoirs, but of course reservoirs are made when a river is dammed, and so it's completely reasonable to create simulations in rivers upstream or downstream of the reservoirs as well. So today, okay. I really want to focus our time on numbers 2 and 3 and 4, but in order to talk about when we would use modeling, when we would not use modeling, when you can save your money and avoid the undertaking of a model, we need to know what modeling is. So we'll talk about this. How does this work? What is it? And then when should we use it? When shouldn't we use it? And what makes modeling successful and useful? I work for Geosyntec consultants, so we sell consulting services to clients, and some of those services are the creation, calibration, and use of models. And so I'm thinking from a perspective of the person who leads the modeling team, like what are we hoping that everybody understands in terms of what's going to make a modeling effort successful? All right, so models represent water bodies in what we call a model grid. So here's Los Vaqueros Reservoir. It's in the East Bay of California. And you can see here that in the left-hand image, which is a screenshot from Google Maps, the dam is at the north end of the reservoir, the upper portion, the upper part of the image. And so the creek was dammed and water flows into it, and we have water supply reservoir, and that's good. And then in the middle image, you can see the map view of how the reservoir has been divided into a model grid, little squares. And you can kind of see, if you can see my mouse, the model grid necessarily extends outside the wet area that you see in the map, because we want to make sure that we understand the slope of the land slightly up above the water level in case the water ever got that high. The models get very unhappy when you try to put more water into a reservoir than can actually fit in the reservoir as you have defined it in the software. And then on the right-hand side, we see a three-dimensional representation, and this is just a color map showing grid elevation. So of course, it's trending very nicely across the colors of the rainbow from bottom to top. And so this is a three-dimensional model because we have separate squares representing depth, representing distance from the dam, and representing distance across the reach of the reservoir. So when we have a model grid, that is the basis for computation for the model. And so for every one of these little model cells, equations are solved repeatedly. Modeling software solves equations for conservation of momentum so that we can describe water motion, so that we can describe currents that are moving through the reservoir, conservation of heat to calculate temperature, conservation of mass to calculate chemical concentrations, maybe for something like phosphorus. And these calculations are repeated for every time step. Time steps, the length of time steps vary, but they're quite short. A 1 hour time step is quite long. And that would be and the software is actually smart enough to vary the length of the time step based on how rapidly the conditions are changing in the body of water. And so after each time step, the water velocity, the heat, and the mass of chemicals are different due to external forcings, which we'll talk about on the next slide. So the calculations are repeated. But to summarize it here, external forcings are like the river flowing in. As the river flow rate changes, you'll have a different velocity of water entering the upstream end of the reservoir. So you need to recalculate the momentum at every cell all throughout the reservoir at every time step. And so this is called a numerical model because we're doing these calculations over and over and over, as opposed to what we would call an analytical model, where you can fit a single equation to describe the behavior of a system at any location. It's also not a statistical model because the many equations that are in this software are based on physics and chemistry of how lakes behave. And so this is the formalization and the mathematical representation of limnological principles in the software. So models are built by creating input files. The software comes knowing all of these equations. And you could make your own if you wanted to, but there's been decades of work going into refining the software packages that do exist. And so often when one is doing this modeling, one is not developing a new model, but one is creating a model for a specific water body. And models need to know about the influences on the reservoirs. So these are specified at their boundaries. And I like to think about it as above, below, upstream, downstream, and to the sides. And that's what's meant to be represented here. The flow in this reservoir that I drew out using PowerPoint, artistic tools. You can tell that I'm not the world's greatest PowerPoint artist, but hopefully you get the idea that water is flowing from the upper right to the lower left. There's a concrete dam in the way, and there's a reservoir that's filling up the river canyon behind that. We've got, little streams flowing in. Those are the tributaries kind of on the sides. So we need to tell the model what is entering the reservoir from upstream and from the tributaries. If you'd like the model to simulate flow, then you need to tell it the river inflow. If you'd like the model to simulate temperature, then you need to tell it the temperature of those river inflows. If you'd like it to simulate nitrate, you need to tell it the nitrate concentration in those river inflows. So here's a take-home point that I want to make sure it comes across. These models are not simulating what's going on in the watershed upstream of the reservoir, the lake, or the main stem of the river that we're simulating. Those are input files. So often we'll talk to clients and colleagues and we'll say, oh, great, we'll make a model. Can you send us the data that you have? And they say, why do we need so much data? I thought your model was going to tell me the temperature of the reservoir. And we say, yes, we're not actually asking for those data right now, that we will in a minute, and I'll tell you why. We're asking for the data around the reservoir so we know what's going to force, what's going to be the external influences on the temperature of the reservoir. Bathymetry is also quite important. Meteorology is also quite important. And we have to know the dam outflows that are letting the water move downstream as well. These all together are what we call boundary conditions because they are the time series of changing conditions that are happening at the boundaries of the reservoir. So the consequences of this are that numerical models can only be run for the time when input time series exist. If you have flow measured by a USGS gauge that came online in 2021, then we're going to simulate your reservoir from 2021 onward. And otherwise, we can estimate flow in the main river in 2018 and 19 and 2020 or something like that. But those will be flow estimates, and so the model of the reservoir will be less certain as a result because we won't be sure about the flows that we're putting into it. To predict future conditions, then it's necessary to predict the weather and the inflows, and thus these models are used for prediction really only as far out as we're confident in the prediction of those boundary conditions, most notably the weather. Then the model must be calibrated before use. Calibration is the adjustment of model inputs and parameters so that model output matches field observations. So here we do actually hope to have temperature of the water in the reservoir so that we can compare the model output to measured data and make adjustments to the model so that it's the best representation of reality that we can have. We calibrate in order. First, we begin with water balance. We need to have the right amount of water, the right flow through the reservoir. Then we calibrate temperature because this is representative of circulation processes. The real gold standard would be to have sensors in the reservoir that are measuring water velocity, like how fast is the surface water current moving through the reservoir, how fast is the bottom water current moving. And I should say again, this is the same for lakes, this is the same for rivers. We're focused on reservoirs today because they're a bit more complex. They're like part lake and part river, but certainly these concepts extend, and it's certainly so with respect to a river. If you can measure the water velocity, the model can tell you these things, and that's a very nice data set to be able to compare the model output to. And then, of course, we're hoping for calibration data for water quality variables of interest. Well-constrained variables are left alone. If we have a meteorological station right on the reservoir, the best would be on a floating platform in the middle of the reservoir so we know the wind that is right at the surface of the water. Then if we trust that wind sensor, that anemometer, we're just going to put those wind time series data directly into the model. But if, for example, we're using the wind measurements at the nearest airport that might be 25 miles away and might be on the other side of some hills, well, in that case, we're kind of thinking, the solar radiation at that airport is probably roughly the same as what's experienced on the water surface of the reservoir, but maybe the wind is not. And so then we would say, maybe we need to make some adjustments. Maybe we'll say at all times in the model, the wind on the reservoir is 10% greater than the wind experienced at the airport some distance away. So when a variable is not well constrained, that might be something we vary during calibration. And we have to use a bit of a sense about like how much is reasonable. I mean, if the model is indicating that it won't calibrate unless the wind on the reservoir is 3 times as fast as at the airport, really? And the airport is experiencing, 25-mile-an-hour winds. You're saying that the reservoir was experiencing 75-mile-an-hour winds? That's a little hard to believe. Maybe there's another process here that we haven't thought of. So that's what I mean when I say uncertain variables are varied within a reasonable range. All right, so model output comes in 4 main forms. I want to show some examples of what comes out of these models. Here we're looking at vertical profiles. These show us many depths at one time and one location. Now, that's just how we chose to make these figures. The model can tell us any depth, any location, any time within the domain, the geographical domain that was modeled, and within the time that was simulated. So if you want to run your model from 2020 to the end of 2022, the model can tell you the conditions that were simulated in any cell in the model at any time step throughout that duration. We've chosen, we usually choose to put the vertical profiles in the places where monitoring personnel have gone on a boat and lowered their sonde in the water column. So that's what's going on here in these plots. We have observed data in the white squares that have black borders, I mean, you could say they're black squares with a white center. And then we've got model output in the gray circles connected by a gray line. And you can see in this mid-reservoir location on the left side, we're simulating surface water pretty well, but the bottom water is too cold in the model. And on the dam forebay, we're doing pretty well. There's some details to the shape that's not perfect. Temperature of the bottom water as the water column is warming up in the spring. So if you wanted to improve the calibration at the mid reservoir in mid-June of 2020, the left-hand plot here, you would actually not change things that are occurring in June. You would actually need to change something from probably April, because that's when the bottom water was beginning to warm up. Once stratification sets in, there's not a whole lot that's going to affect the temperature of that bottom water except diffusion of heat from above. Let's see. So second type of model output is a time series. You can show model output at any location at one depth or at many times, and that can be quite interesting. And intentionally in this presentation, it's super tempting to put together a presentation for all of you that looks great, where every plot is ideal, and you say, here I am, I'm the modeling consultant, and when I touch the models, they look really good. But I'm intentionally selecting figures that don't look good so that we can talk about kind of the bumps in the road that one hits. And this figure is showing that. This figure is not one. So I said in the gray text, one depth and one location, and really this is actually a time series of the water leaving the dam, and the black is the observed data. The red is the simulated temperatures that are entering the penstock opening on the upstream end of the dam. So we're assuming they don't change as they flow through the penstock. And wow, okay, so right in the sort of center left of the screen, temperature matching is really pretty good in January and April. We have some variations in temperatures, but both are in the same range as we get into like May and June. And then, oh my gosh, what's going on in August of 2020? Well, one of the things that you have to watch out for when you work with modelers is whenever we see a poor model data agreement, one of the first things we say is, I don't know, are those data accurate? Maybe there's a problem with the data, because wouldn't it be nice if the model was right all along and we just fixed some, error in the data and now everything's perfect and we didn't have to puzzle over the model. And we're not trying to be lazy. It's more actually that it's really not very pleasant to work hard trying to calibrate a model and to try to get it closer to matching a target, only to find out later that the target wasn't correct and the target has to be moved, because then you find out, oh man, we have to fix the model all over again. And so when you see this kind of disagreement where the model and the data are this far apart, you say, really, are these data legit? It turns out that in this case, the answer is no. And there's diurnal fluctuations in this temperature that's observed about 200 feet downstream of the dam outflow. And so it's not only diurnal, it's actually the temperature spikes whenever the dam outflows drop below about 1500 CFS. And the question is, what's going on here? And it turns out that the water is actually heating up due to surface heating, because the residence time in that reach of the dam tail race is too long for the observed data to be measuring the same temperature as the temperature of the water when it was sucked from the reservoir into the penstocks. Neither of these lines are wrong. They're just not measurements of the same thing. And so this is a time when we don't see good agreement between the model and the data, but that's explainable, that's forgivable, and it does not immediately mean that the model needs to be changed. All right, so here are a third type of model output. We call this distance depth contours, and this is a little bit more abstract, so I'll try to step through it. if you look at the horizontal axis at the bottom of your screen towards the right, river mile 105 is where the dam is, and we're looking upstream to the left. So the river inflow is all the way on the left side of each panel. But this reservoir has a side arm that comes in. So how do we show that? That's the colored area you see all the way to the right of each panel, and that enters about 2 miles upstream of the dam where you see one of those arrows coming down. What we can show here is the temperature in every model grid cell at different at all locations at one time, all depths at one time, but one time for each plot. But of course, if I put 3 plots, you can see that the reservoir is quite stratified in the summertime, and then we can see the water cooling off in October, and vertical mixing is almost fully complete. The water column is almost fully mixed by November. Okay. And then finally, a fourth one, we can have map contours. This is particularly useful for shallow lakes where we assume there's not a whole lot of variation in the water column. We're just looking straight down. We can put this very nicely on a map. This can be combined with GIS mapping. And this is much more interesting for 3-dimensional models like that one we saw before and that one we saw here. I do believe this model actually has, this is not a guess, it is a fact that this model is a 3-dimensional model. It has a representation of discrete depths, but there's just not a whole lot of variation over depth. And in this case, this is about sediment deposition and the median thickness of sediment deposition recorded over the length of the model runtime. So there's a turbid river coming in from the lower right, the southeast on this one, and so we can see where the sediment is depositing. And we're not that surprised to see that a lot of the sediment is moving all the way to the dam, the fine particles, and that's where they settle out. Okay, fine. Modeling is, why would we do this? We should simulate reservoirs with models for 3 reasons. First, it is extraordinarily helpful for understanding limnology thoroughly. Here's an example. This is Kensico Reservoir in New York. It's in Westchester County, just north of New York City. It is the last storage reservoir before the municipal drinking water supply gets to New York City. So it's coming from, if anybody's ever studied this system, you can correct me when I say this incorrectly, 19 reservoirs in the Delaware system and the Catskill system. 2 aqueducts feed in. One is I'm just doing with the blue arrow, and one I'm doing with the orange arrow. And then both aqueducts actually leave pretty close to where the green arrow is to head down to New York City. And you can tell it's right next to Westchester County Airport if in case you want to look this up on a map yourself. And so we simulate this with a model, and it turns out that one of the aqueducts has a warmer temperature than the other aqueduct. So what happens to the water? Does the water mix? Is the Rye Lakeside in the southeast, does that water kind of just stay down there? It turns out no, not at all. Because the water coming in from the east side is warmer, it floats on the surface, and a fair fraction of it, when it gets to the confluence of the 2 arms of the reservoir, turns upstream. It is not pushed back downstream by the water coming from the north, because that water is colder, so it plunges to the bottom of the reservoir, which you can correct me on this too. I think it's like 120 feet deep or something like that. Anyway, it's deep enough for the northern tributary for that water to plunge beneath. And that water actually turns into the eastern side of the reservoir some distance. Yes, of course, they both do mix, and you cannot tell one from the other when it's leaving the reservoir at the southern side. This is something that field personnel could figure out if they knew exactly what to look for, if they were clever with their data analysis back when they got back to their desks. But when we run the model, we see this pretty evidently as soon as we make the model output that allows us to see this kind of thing. And then this matters, right? There's applications for mixing matters for turbidity transport, because if a storm leads to turbidity in one aqueduct system but not the other, then it's nice to know where the turbidity particles are going to go. Here is Chickamauga Reservoir in eastern Tennessee. So water is flowing from the north to the south in the screen. Watts Bar Dam is upstream of Chickamauga Reservoir, which is upstream of Chickamauga Dam. And this is just near the town of Chattanooga, if you're following along on Google Maps. Here, seasonal flow rates out of the upstream and downstream dams exert a dominant influence on water temperature in the reservoir. We can take a model of this reservoir and change lots of other things within reasonable boundaries. Now, I'm not saying we're going to all of a sudden pretend like weather of, Quebec or something like that. But in normal year-to-year variation, the thing that matters that controls the temperature is how much water is flowing through this reservoir. In a wet year, more water flows through because the storage capacity is very low. So if the water's in the Tennessee River, then it needs to flow from Watts Bar down to Chickamauga Dam and on further west. But the model was, we were able to use the model to kind of demonstrate what is the dominant influence on temperature in the reservoir. And that matters because there's a thermal power plant that uses this reservoir for cooling water. And so the thermal power plant folks care very much about the temperature of the water in the reservoir and what's influencing that. It's their cooling water, and that affects how much electricity they can generate. Another reason to make a computer model is when we need to simulate scenarios. This is probably the biggest, most important one. Common scenarios: FERC licensees, hydropower dams might simulate the effects of climate change on temperature leaving a dam if they have a temperature compliance requirement in their license. And they might also look at the effect of altered dam operations, maybe process flows or minimum in-stream flows on temperature downstream, with temperature as a water quality variable that then influences fish habitat. This is what I'm spending the vast majority of my time doing. Water utilities might simulate circulation and water quality effect of a new withdrawal or a new industrial or wastewater treatment plant discharge. A colleague of mine here at Geosyntec years ago did the modeling of Lake Mead. So on the right-hand side of the screen is Boulder Basin. On the downstream end of Lake Mead, you can see the note for Hoover Dam. Hopefully people are relatively familiar with this area. That's Henderson, Nevada. You see the word for Henderson. This is just outside Las Vegas, which is just to the west and northwest. So I can't remember exactly where the wastewater treatment plant discharged. So my marker line is approximate, but the point is it goes into Las Vegas Wash, which goes into the western end of Boulder Bay. Would still be as unlikely as possible to go into the drinking water intake. A third reason is when we need to forecast the future. I talked about this a bit more earlier. And forecasts are limited by input data like meteorology and flow, as well as model runtime. So the forecasts tend to be used for two-dimensional models because they run much faster than and they tend to be used for regulatory compliance. So we have a dry spell coming. It's going to be hot and dry for the next 7 days. Can we run that through the model and see if the temperatures in our reservoir are going to rise to the point where we might have a problem with temperature compliance within the reservoir? Not all reservoirs need a model. If you're someone who is skeptical and saying, I know this is fancy, I also know that it's expensive to do the work to put these models together and use them. Both statements are true. So can we get out of this? Do we really have to spend this money? Here's when you would not get into this. Or you would do it in a phased approach. You would say, let's take another approach first, go a little ways, and then see if there's questions that we can only answer with a model. First is when a robust monitoring data set is enough. If you simply need a characterization of temperature in your reservoir over the last 5 years and you have a reservoir monitoring program, or like I said, a lake monitoring program or a river monitoring program, then use your data and summarize it and make good figures, make a database, That's great. And if that is what you need to characterize and satisfy the regulator who might be interested or satisfy the stakeholder group, then a model is likely not necessary. The question then would be, are monitoring data collected at sufficient spatial and temporal resolution? Do you know what's coming out the dam? Do you know what's at that important part of the reservoir that might be used for recreation? Would a model add anything in terms of the understanding I mentioned on the slides that came before? If no scenarios or applications need to be tested, then that's a time when maybe a model is not necessary. The idea here is that the beauty of models is that they allow us to test things and do experiments that we could not do in real life. If that need doesn't exist, then we don't necessarily need a model. You also would not have a reservoir model, a reservoir water quality model, if what's really needed is a hydrology model or an operations model. Now, the distinction here is that a hydrology model tells you how much river runoff you get given land slope and infiltration rates and precipitation patterns. All right. And that's also a numerical model. It's just not a reservoir water quality model. You would not do the water quality modeling that I'm talking about to know if your reservoir is going to hold enough water for the supply to the city, even though it's a low snowpack year this year in Washington. That would be a hydrology model or a reservoir operations model. This goes back to what I was saying before. These numerical water quality models don't simulate the inflows to the reservoirs. They simulate the characteristics of the reservoirs. Simpler models simulate responses of storage volume, water level, and power generation to inflows and water demand. And these are often precursors to water quality models. I'm working on a project now where the folks who have the operations models say, okay, it looks like we want to operate the reservoir this way. Now take that scenario and run it through the water quality model to see if that would lead to perturbations in the water quality. Then let's see here. I was going to say, otherwise, it's a watershed model that would be needed to understand how much water is coming in. And yes, you can certainly couple watershed modeling to create the inflows from the tributaries that would then flow into the reservoir to understand what happens to the water quality of the water in the reservoir when it's there. All right, so what leads to a successful modeling effort? You say this sounds great, you want to work with a team to create one of these models. As the modelers, we hope to have data. And we'd really like to see it early in the modeling process. It's really not that fun to be spending, weeks estimating dam outflows and then to find out, oh, here's some measurements. It just leads to rework and it leads to increased expense and inefficiency. If we don't have much data, we're going to ask things like, can we conduct a monitoring program for a year or two first? Could we, plan this out and make a work plan in 2024 and monitor in 2025 and 2026, and then start the modeling effort in the winter of 2026? Because then we would have the inflow data and the calibration data that we would need. Otherwise, we might need to make guesses that will impair our calibration and add uncertainty to scenario results. And it's our job to try to make clear, if this is uncertain here and you need scenarios that do this, like what's that trade-off look like? And then will you be happy with a description of general trends? If we don't have a lot of data, then the model is going to be a little bit less certain, but it's going to tell us something. So then the question becomes, is that enough, or do we need to be really precise? We'd also like to have organized data. Monitoring programs might have just lots of files in lots of folders, especially if there's been changeover of personnel, and they might say, okay, here's a zip folder of 94 different files. I'm not sure what's in it. You can take a look. Go for it, modelers. Well, we're going to ask if we can make a database and we can put it all in one place. And we are very much in favor of the modeling team being the ones to organize the data, because we know what we're looking for. And if other folks create it, it could work fine. We'd at least like to have a chance to talk to them. I would also say that in this case, if you're going to have the modeling team look through the limnology data, the modeling team ought to have a limnologist who understands what they're looking at. Sometimes modeling teams say, yeah, we have experienced modelers. That's good. do you have experience in understanding, lake processes and the data of the lake processes, so that the connection between, ammonia production and biological growth and pH and dissolved oxygen all connect, instead of those just being individual data sets that need to get sort of blindly put into a database? It's a good idea a lot of the times for a complicated project to write a quality assurance project plan. This can be required if this is going to be a model reviewed by the state of Washington Department of Ecology or other regulators. But it's really great to have everybody defining goals, calibration targets, and planned applications. And for clients to read that carefully and understand what targets the modelers are aiming for and why, so that we're all on the same page about what the model is going to be used for. Because if the model doesn't work so well at a certain time, one of the first things we'll say is, does it need to work well at that time, or is that a time that's maybe less important? Obviously, sometimes it's clear the model needs to be better, we need to fix it, we need to improve it. But in terms of regulatory compliance, for example, sometimes are more important than others. Obviously, in the summer and in the early fall is perhaps one of the most important times for temperature compliance. And in winter, none of our rivers are too warm in the winter. So if the model's not perfectly simulating the temperature of the river in the winter, that's okay. Uh, I'm working with a client right now that is, they want to put off the start of modeling, but then later we might need it. And it's kind of making me a little nervous, because the model, you can't just snap your fingers and have it finished and ready to go. So in that case, it does take time to actually do the modeling and to do the calibration. Model development and calibration for a complex reservoir can take the better part of a year or more. Scenario analyses can take several weeks. And sometimes, especially for 3D modeling, model runtime is important. I'm working on a project right now where running the model for 20 years of simulation time, so the model is describing 20 years at the water body that's being modeled, takes 3 weeks of real lifetime with the computer just sitting there running. So you're talking about one set of model runs each month. And that means you need to be fairly careful and fairly strategic. It also means you need to understand that if you want to have these scenarios run, we're talking about, all right, we're talking about that on April 18th, like we should have results before Memorial Day. And if you don't like them, then we will make sure to have results by the end of June. And that's right there, a couple months in the schedule. Three-dimensional modeling is a different world than two-dimensional modeling because of these model runtimes. But also, when the model takes overnight to run and you can only do one iteration per day, or a batch of 8 iterations that all go overnight, and then you look at them the next day, you can't just instantly work harder, because sometimes you're waiting for the computer to do it. And then we hope to have limnological understanding. If there's things about your reservoir, characteristics that that we don't, like, don't believe that meteorological station, it gets real windy here every afternoon. We really like knowing those types of stories. Is it really every afternoon, or are those the ones that just stick in your memory? Did the reservoir freeze last winter? What about the winter before? Well, no one was out there, I know that, and the road was full of snow, so we couldn't get up in the mountains to look at it. But do we think it freezes more often? I mean, you folks are the ones that own the reservoirs, and so the extent to which we can kind of understand, oh, there's a cofferdam 500 meters upstream, it's 50 feet high, and that's the cofferdam that was created when the large dam that creates the reservoir was being built. You need to realize that's an important feature on the bottom of the reservoir. Those types of nuggets of limnological understanding are a very big deal to us. All right, so let's talk about questions. Here's questions that I have when I think about this stuff. Lately, I've been thinking about AI. I'm certainly not the only one. And my question is, to what extent can this water quality modeling be replaced by AI? It's a lot of work. Can computers just do it for us? There's firms out there that are using AI to predict stream flow given weather forecasts and other factors. This is not numerical modeling. They'll talk about training the AI model, but they know precipitation and they know stream flow. And so if you get this much precipitation in 500 watersheds, we know that watershed number 501, when it gets this much precipitation, it'll probably get this much stream flow. There are no hydrological equations. The AI models don't contain any principles of runoff or soil moisture storage or land cover or any of that. But those predictions tend to be robust and accurate and useful. Here's your stream flow for the next 5 days based on the weather forecast. And you can run this every day. So this is changing the world of watershed modeling. Do we need to do a numerical watershed model anymore now that AI can help in these ways? Can water quality modeling experience the same innovation? What would that look like, and what would be the trade-offs? I'm not sure the training data sets are sufficiently robust, and that the predictive ability of the next 5 days is my reservoir going to be warm on the surface over the next 5 days? Maybe that predictive need isn't there. Those are the questions I have on my mind, and if anyone has thoughts on them, I'd be super curious what you have to say. Otherwise, I welcome your questions as well. I put my contact information down here if anything I've said is particularly interesting, and Giovanna's is down here. If there's any difficulty reaching me, you can reach her and we'll get in touch.
Well, thank you. Hope everybody can hear me.
I hear you, Giovanna.
I don't see any question in the chat box. I'm gonna turn to the audience here if there is a question.
Yeah, here is one question I have, Rich. Thank you for the good presentation. You said that you're talking about 3D numerical modeling. Do you mind sharing which modeling software are you using for modeling?
Yeah, Anurag, sure. It's EFDC is the software. So generally, EFDC is the Environmental Fluid Dynamics Code. It is EPA approved for the use at Superfund sites, and that makes it the go-to for a lot of three-dimensional modeling because it's well known by regulators. There's another one called AEM3D, which is certainly useful, that was created at the University of Western Australia. Gosh, 20, 30 years ago. It had a different name. It was called LCOM. When there was the water quality model was CADM, but then it got renamed into AEM3D, and it has its applications as well. In 2 dimensions, the accepted software is something called CE Qual W2, which is maintained by Portland State University under contract to the Army Corps of Engineers, and it is also quite commonly accepted by regulators.
Just one question. I mean, it's probably getting into more of the weeds. If somebody else has questions, please feel free to ask, and I'll just stop. Yeah, I was just thinking about the 20-year time period, and it's taking, like you said, 3 weeks. And I was just, that's why I wanted to know which software you're using. It's interesting that it's taking 3 weeks, but
yeah, sure. I mean, we can talk about that. We can talk about that more offline. I can tell you all about that project.
Yeah. I let other people speak. Yeah.
Thank you. And as well, I want to thank you, Rich, for this very informative presentation. As everybody else in the chat gathers their thoughts, I did have a question when you showed us the observed and predicted temperature in your calibration. I think one of the first slide. I was wondering if the values in the predicted temperature, they also have an accounting of modeling errors, and maybe there is some variability in those prediction in the model output data.
The audio just didn't come through. If they have an accounting of modeling, what?
Errors.
Oh,
yes.
I mean,
if those dots are actually have a standard deviation or an error that puts them into a range of temperature.
Yeah, so it's a great question. This is a deterministic model. These are equations that have one answer. And so the model itself doesn't have error, but there is uncertainty in the input data. And so if, let's pretend that our solar radiation sensor was accurate within 5%, So we have a number of, for the solar radiation, the sunshine shining on the water surface, that could be plus or minus 5%. The way to represent that here is to run the model and then run it again with solar radiation 5% lower, and then run it again with solar radiation 5% higher, and use that second model run and the third model run to create new output and characterize that output not as a new line, but as error bars around the gray line that you see here. There's nothing,
So
there's nothing probabilistic in the actual software. And so we characterize our uncertainty by actually representing that uncertainty in our input data sets or in the parameters, and then rerunning the model to see how much it's going to vary.
I see, thank you. So it's like having different scenario with worst case condition or different case condition.
Yeah, that's exactly right. And there's so many different inputs that it's not actually practical to do what I just said. So instead, what we've done is a series of what we call bounding analyses. We get the best model that we have, and then we sort of ran it for like the warmer worst case, where temperature is higher and solar radiation is higher and air temperature is higher, water temperature is higher, and that sort of thing. And then the colder worst case to say, you know, how much warmer would the reservoir water be if everything was not necessarily correct and there was, based on the variation that we know is there in some of these input files. That's one way to do it, but this is where it can be more art than science, and this is where modelers can really discuss back and forth. What I just said is not likely. It is not likely that our solar radiation sensor would be 5% warmer, and our temperature sensor of the air would be 5% warmer, and our river temperature measurements would be off by a little bit. So if I run that model scenario, it's not a reasonable scenario, but it might show, you know, if everything was wrong and our surface water temperatures would be 1 degree warmer, that's kind of nice to know, because everything is probably not wrong, and that's the amount of uncertainty that you could expect based on all of the inputs.
Thank you. I don't see other question in the chat box. So unless Samira here has another one, I will ask you in your experience modeling reservoirs, assuming a similar temperature condition, because as I understanding, or similar latitude, and so external temperature condition. As I understand, this might be a very important factor for the temperature in the reservoir. What other parameters are more likely to impact the temperature simulation?
Yeah, sure. It's a great question. The other one is the residence time of the water in the reservoir, which can be, I mean, ultimately is a function of, I mean, residence time is the volume of the reservoir divided by the flow through the reservoir. So small reservoirs will fluctuate in temperature a lot. They have very little thermal inertia. And large reservoirs that have large flow moving through them, this is where we need to remember that a lake that contains a certain volume of water tends to have a much higher residence time than a reservoir that contains that certain volume of water, because that lake is usually from a natural basin in the earth, and that reservoir of the same size, if it's a large reservoir, is probably blocking a large river, and so it will have a much lower residence time. And that residence time in our area will vary substantially throughout the year, because flows are low in the late summer and flows are high when the snow is melting. So the meteorological variables that you mentioned are going to act to warm up the water, but the residence time of the water is another major constraint on the actual temperature that ends up coming out the dam. Oh, and then the next one is the depth of the withdrawal from the reservoir, because as we were talking about on this slide, you can see the two arrows on the right-hand side where it's just kind of below where it says dam. The deeper one is the penstocks for the power plant. And you can see that even in the summer when the reservoir is stratified and the surface water is hot and pleasant for swimming, it's still sending cold water downstream. If you use the spillway at the top of the reservoir, then you'd be sending warm water downstream. And so in terms of what's controlling the temperature of the water below the dam, it's hugely important what depth the water is taken from.
That makes a lot of sense. Well, thank you, Rich. I'm gonna stop our recording now. And thank you everyone for attending this